In this series, I'm going to be utilizing a model known as Frenet-Serret, which characterizes a particle in Euclidean space. And I'll be using Cartesian coordinates x, y, and z to characterize a function that describes a path followed by the particle, which will be seen as a curve. So I've already laid out some initial groundwork for us to work from. So starting off, this curve function that I've created uses 3 input values to return an array which contains values that describe points in space, x, y, and z. So this curve takes a time input value, as I've characterized up here, which is a linear spaced array from 0 to 4 pi, and it's discretized into 36 separate positions, along with an r value here, which I chose to be a constant 3. This will be used to basically extend out trigonometric values to, give them a value greater than something between 0 and 1. And this constant mz value here, which is also just a constant term, and that will describe the rate of change of the function with respect to the z direction. So that's what's going to be giving this path. You'll see it's something that looks like a circle, but it'll look like it's stretched to almost look like a spring. So this first function here defines our curve in Cartesian coordinates, as I said, and utilizes the t, r, and mz. So this array x, y, and z that's being defined here, you can see it's separated by 2 columns to create kind of 3 independent identities. So in this first section, this will characterize our x coordinates, our y coordinates, and z coordinates. So our x coordinates, cosine of t. So cosine is a function of time, and it will be multiplied by that r value to give it that magnitude. Similarly, the y positions will be using sine and r in basically exactly the same way. And then our z values will just be that constant mz multiplied by time. So this function will return x, y, and z, which I've stored in a variable x, y, and z right here. So make sure to run everything here. And if I just take a look at what x, y, z is looking like here, you can see 3 distinct regions in this matrices. So here's our x values, our y values, and our z values. So clear this. The next thing I want to do is, well, really, it probably would be helpful to have a visual. So let's just plot this initial curve and see what it's looking like. So we'll do that. Rows equals 1. And we'll want to specify this. Cool trick, you can put a function or a library in Colab if you're using it. Use a question mark, and it will give you some basic literature to help you. Specs, and 2 brackets. So we want lines and surface. See if that works. Plus line. Now I think the type is what we want. Okay. And then let's get our points on this at scatter. We want it 3D. That's right. So x will equal our XYZ array at the first position for all of those values. Y similarly will be XYZ, the second position for all values. And Z will be X, Y, and Z, the second position for all those values. Whoa. It's not looking... Ah, yeah, it wasn't looking 3D there. So hopefully that should fix that. Okay, cool. So there's this curve in 3D space. Also, update. Just want to change the layout of this a little bit. Poly_dark, that should be it. Cool. Okay. So now that we kind of have our curve characterized here, this is what we'll use for the rest of the series to look at some things here. And the first thing I want to go to is the concept of a Jacobian. So a Jacobian matrix can be used to basically take a high resolution snapshot, like using the concept of calculus. If you keep going down to infinitesimal lengths or units, you can kind of consider things as linear at that kind of resolution. So we basically want to create a Jacobian, which is a matrix that contains partial derivatives with respect to independent variables. So we're going to want to create a function here. So let's get this out of the way. And let's call this, we need to define it first. Let's get our Jacobian from a given function. So we'll use our curve basically kind of to define this. So we'll use it as an argument. But first we need to kind of numerically, we need to basically find the derivative, the rate of change, because there's some differential change with respect to dependent and independent variables. That's what the Jacobian matrix is made of, right? So we probably maybe call it differential. And I'm just going to do a pretty, traditional numerical differentiation. So we'll come up with the idea of giving an x naught and some small differential x value. So that could be pretty small. We could do to the -9th. So then we probably, since we're dealing with arrays and matrices here, we want to keep things in that form if possible and avoid just using scalars. So I'm going to define this single value, but I want it within an array. So there's a function that numpy has that I imported earlier. So I'm going to import numpy dot at least 1d. And I'm going to supply that initial value. And then to describe basically we need to create a storage space for our Jacobian matrices, which is dependent on the function we're supplying and the number of independent variables there are. So we can say this all we need is one, basically that evaluated it at one time value, because in our case we only have one independent variable. So let's just evaluate f at t equals 0 essentially. So in a similar fashion, we want this to also be one-dimensional, but we want to supply our function evaluated at x of 0, right? Is that one too many parentheses? Yeah. So now we can kind of create like a matrix of zeros now, following that same idea of having like storage space to work through things. So what is the size of this going to be? Well, if we think about our number of rows should be the number of dependent variables. So that for us, that's x, y, and z, because x, y, and z are changing all with respect to t. So that's 3 values. So we want an MP zeros uses. Okay, yeah, we need to supply a tuple. So we want our f naught size, right? Because when we evaluate that initial function, that should give us 3 values, and then we would just want our x naught. Yeah. So then from here we can go through and basically do like sweeping math. Oh. Okay, back, have our connection. So basically we're going to do like a sweeping form. If there were multiple independent variables, that would characterize how many columns we would have for a Jacobian matrix. Since we only have one independent variable time, in our case there's only going to be one column, but it's good to be kind of have a robust process as we're creating. So we have this J now that's been created. So we want to loop through range, and we only have one column. So we want to go to that size. I think Python, yeah. Okay. So here's where we'll loop through and do the actual grunt work. So we don't want to be changing. Basically, want to create a copy of x naught, because I don't want to be changing that. I want to keep that as the same. So we'll create a copy, and similarly, how do we want to do this? Well, that's stored. So when this goes through the loop initially, we can refer to it at that position and add on that differential x as part of our numerical differentiation method. And now we can start doing this array kind of broadcasting. So we want to, since we're kind of doing a sweeping operation, we'll do all rows for column I, and we want to have, should be our f of x minus that initial, which will be, well, we already stored that, should be f naught. And then that should be divided by that differential length, and that should be good. Okay, we can return that. We can return that j. We can return diff. Valid syntax. Here. I'm not sure what's wrong there. Not sure why that is happening. Well, this is supposed to. That's why. Okay, I had a bit of a hiccup there, but it took me a lot longer to figure out than it should have. So now, basically, at this stage, we can determine our Jacobian function. So really, all we have to do is what do we want to call this? Get Jack, and we can use lambda to use our defined function. What do we call it? XYZ equals curve. So we can use curve, and this will basically get the math done with MZ staying the same. So this should give us a function. Okay, so let's just call that Jacobian and store that. So now if we evaluate at some value of time, we should get a value. Oh, duh, gotta type in a number. What about at like 0, 1? Interesting. Zeros. So it's like these aren't being changed. That's why. Okay. When I put these numbers in without the period, it was not taking it as a floating value. So that's what we get if it's 1, for example. And what about 0? Okay. So we get a number there. So to kind of verify if this is working correctly, I imported Jax, and within Jax there's a function created like native to Jax, so you can basically bypass the whole function that I just created and go right into using this function. It's already been made for you. So Jax.Jacobian, and we'll do 0. See if we get the same thing. Expected a callable value got 0.0. Oh, duh. We have to do something. We have to give it our curve first. We never defined that. So Jax.Jacobian should be just like up here. We have to get our function, so it should be lambda. It's t and use our same curve function. That should give us a function. And let's put this in, let's call it Jack's Jacobian. So now that we have that function stored, let's put in 0 just like we did up here. And we should get the same value. It's not defined. What? Oh, spelled it wrong. Yeah, and then let's change the shape. Yep. Okay. So we can do, other numbers. They should be the same. Perfect. So moving forward, if we're going to call a Jacobian, it'd obviously be much easier to just use the one built in Jax. So in the next part, I'm going to go into a method of characterizing the curve using unit vectors that are tangent and normal to the curve.